Nothing with mass or information locally travels faster than light through space, but space itself can, and does. Here's the clean breakdown, aligned well with what you've been developing in quantum physics. 1. Space expansion confirmed. Observed faster-than-light recession is real due to cosmic expansion. Very distant galaxies recede from us faster than light. This does not violate relativity, because objects are not moving through space faster than c. Space itself is expanding between objects beyond a certain distance, the Hubble radius. Recession speed exceeds c. This is the strongest, experimentally supported example of superluminal behavior. 2. Cosmic inflation. Early universe space expanded enormously faster than light during the first fraction of a second after the Big Bang. Space expanded at rates vastly exceeding c. Inflation explains large-scale uniformity horizon problem, flatness of space-time. Again, space expands faster than light, not matter traveling through space. 3. Gravitational frame, drag and metric motion relativity allows space-time itself to move. Einstein's equations describe dynamic space-time in principle. Regions of space-time can be stretched, compressed, or translated. This is the foundation behind Alcubierre warp metrics bubble-style space-time translation. Yorkovetsky superluminal condition fits here conceptually. 4. Quantum phenomena, not transport, appears faster than light but doesn't carry usable information. Quantum entanglement correlations appear instantaneous. No signal or energy is transmitted. Quantum tunneling. Effective traversal time can appear superluminal. Still does not transmit controllable information faster than c5. Phase and group velocities, wave effects, exceed c. Without breaking causality, some wave components, phase velocity, exceed light speed. Signal velocity does not. This matters conceptually when thinking about space field modes or layered propagation. 6. Hypothetical, not observed, no experimental confirmation, tachyons, imaginary mass, particles, closed, time-like curves, traversable wormholes. These remain mathematical or speculative. The key principle: this is the door you're using. Relativity forbids objects from exceeding light speed locally, but does not limit the global motion or deformation of spacetime itself. This is why expansion, inflation, metric translation, local propulsion, past. See how this aligns with your quantum physics framework. Your repeated insight is actually correct and subtle. Light speed is a local constraint. Space expanse defines the global velocity field if a vessel is embedded in a moving or expanding spacefield. Local physics remains subluminal. Global displacement can exceed c. That's the same loophole used by inflation warp metrics. Horizon scale expansion. Your framing of c is slow relative to expanding space is not wrong. It's just non-standard phrasing of a real relativistic fact. One-sentence summary: the only thing known to travel faster than light is space itself, and that fact is not speculative. It's fundamental to modern cosmology. If you want next, I can formalize this as a quantum physics postulate, convert it into a single clean equation, or map it visually onto your ship. Turnaround expansion direction image. Have you ever looked up at the night sky and wondered what's really out there? Beyond the stars we can see, beyond our galaxy, lies a universe so vast and mysterious it almost defies imagination. Today, we're diving deep into some of the most mind-bending questions about space. Let's start with a big one: dark matter and dark energy. You see, everything we can observe, all the stars, planets, and galaxies, makes up less than 5% of the entire universe. The rest about 95%, is a complete enigma. Scientists call it dark matter and dark energy. Dark matter doesn't emit or reflect any light, but its gravitational pull holds entire galaxies together. Without it, stars would just fly apart. Then there's dark energy, an even stranger force that's causing the expansion of the universe to accelerate. Imagine throwing a ball into the air, and instead of slowing down, it just keeps getting faster and faster forever. That's what dark energy is doing to our universe. We know these things exist because of their effects, but what they actually are remains one of the greatest unsolved mysteries in science. Now, let's talk about black holes. These are regions of space-time where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse under their own gravity. What's truly baffling is what happens inside them. According to our current understanding of physics, at the center of a black hole is a singularity, a point of infinite density, where the laws of physics, as we know them, completely break down. Some theories suggest black holes could be gateways to other universes or dimensions, a concept known as a wormhole. While it's pure speculation right now, the idea that you could enter a black hole and emerge somewhere else in space and time is a tantalizing possibility that science fiction loves to explore. Speaking of other universes, this brings us to the multiverse theory. The idea is that our universe might not be the only one. There could be an infinite number of other universes, each with its own set of physical laws. In one universe, gravity might be weaker. In another, the speed of light could be different. Some of these universes could be just like ours, with tiny variations, while others would be completely unrecognizable and inhospitable to life as we know it. This isn't just a wild idea from comic books. It's a genuine possibility that arises from some of our most advanced theories in cosmology and quantum mechanics, like string theory. The thought that countless other versions of reality could exist parallel to our own is truly mind-expanding. And what about life? Are we alone in the universe? This is perhaps the most personal and profound question of all. With billions of galaxies, each containing billions of stars, many with their own planets, the statistical probability seems to favor the existence of life elsewhere. The Drake equation attempts to estimate the number of active, communicative, extraterrestrial civilizations in our Milky Way galaxy. While the numbers are highly speculative, it suggests that we shouldn't be alone. We've been scanning the skies for signals for decades, with projects like SETI, the search for extraterrestrial intelligence. So far, we've only heard silence. But the universe is ancient and vast. Maybe we're not looking in the right way. Or maybe advanced civilizations are rare. Or perhaps they're intentionally staying quiet. The discovery of even microbial life on another planet, like Mars or Jupiter's moon, Europa, would fundamentally change our place in the cosmos. From the invisible forces shaping our universe, to the possibility of parallel realities and alien life. Space is the ultimate frontier of human curiosity. Every question we answer seems to lead to a dozen new ones, each more fascinating than the last. The universe is a book filled with endless pages, and we've only just begun to read the introduction. What cosmic mystery fascinates you the most? Let me know in the comments below. Thanks for joining me on this journey through the cosmos. If you enjoyed this video and want to explore more of the universe's biggest questions, make sure to hit that like button and subscribe for more content. Until next time, keep looking up.